Welcome to Optimization Tutorial 1. This will be a linear algebra recap. A vector space is a set of vectors that holds two operations, vector addition and scalar multiplication. Note that a scalar multiplication doesn't mean multiplying a scalar with a vector, but multiplying two vectors and getting a scalar. A vector space must hold these 7 properties: associativity, commutativity, zero vector, inverse, compatibility, identity, and distributivity. A set of vectors is linearly independent if every linear combination that sums up to 0 of these vectors means that the coefficients of this linear combination are 0. The span of a set of vectors is all vectors that could be achieved from a linear combination of the vectors in the set. The inner product of x and y is a scalar function, meaning it spits out a scalar. Every inner product function satisfies 3 conditions. Conjugate symmetry. If we flip the order of the inner product and take its complex conjugate, we will get the same value. Linearity is as defined here. And positive definiteness, meaning that the inner product of x with x will always be non-negative for every x. And the inner product of x with x would be 0 if and only if x is 0. Some examples of the inner product are the vector inner product, the matrix inner product, and the Q-induced vector inner product. The Cauchy-Schwarz inequality states, for any x and y, the absolute value of the inner product of x and y squared is smaller than the inner product of x with x multiplied by the inner product of y with y. For the case of the induced norm, the absolute value of the inner product of x with y is smaller than the induced norm of x multiplied by the induced norm of y. The proof for that is as follows. For every u and v in V and lambda in C, C is the complex plane, the norm of u minus lambda v is always larger or equal to 0, because the norm of every vector is non-negative. By opening that up using the definition of the induced norm, we get the inner product of u with u minus lambda conjugate multiplied by the inner product of u with v minus lambda multiplied by the inner product of u and v conjugate plus lambda conjugate multiplied by the inner product of v with v. The reason we get lambda conjugate is because by moving lambda from this part of the equation, we need to take its conjugate using the conjugate rule and linearity. This is the same reason that the conjugate is on the inner product in this part and the conjugate is on lambda in this part. That is true for every lambda in C, so we can pick lambda to be this. We can also notice that by the definition of the induced norm of v squared is the inner product of v with v. And so, by plugging that in, we get that the induced norm of u minus lambda v is equal to the induced norm of u squared minus 2 multiplied by the inner product of u with v squared divided by the induced norm of v squared plus the inner product of u with v squared divided by the induced norm of v squared, and that is equal to the induced norm of u squared minus the inner product of u with v squared divided by the induced norm of v squared. That is, because this part cancels out these two. And so, by moving sides, we get this inequality, that the inner product of u and v squared is smaller than the induced norm of u squared multiplied by the induced norm of v squared. By taking the root of this inequality, we would get the Cauchy-Schwarz inequality. The adjoint transformation. Given a linear transformation A, the adjoint transformation denoted by A star is a transformation that is defined by the relation that the inner product of A of x with y is equal to the inner product of x with a star of y. Question number 1. Using the inner product defined by the inner product of x as y is x transpose y. Find the adjoint operator of A, which A of x is A multiplied by x, where x is an m-dimensional vector, y is an n-dimensional vector, and A is a matrix of m by n. Before viewing the solution, I advise you to try to solve it by yourself. The solution. We know that the inner product of ax and y is ax transpose y, which is x transpose A transpose y. If we look at A transpose y as just one vector, we can look at this multiplication as an inner product between x and A transpose y. That means that A star is A transpose. Norm. A norm on a vector space V is a function from V to R, satisfying non-negativity, homogeneity, and the triangle inequality. All of these are on your screen. Some examples of norms are as follows. The LP norm is summing the absolute values of all the members of x raised to the power of p, and then taking the inverse power of p. The L1 and L2 norm are defined this way. The L infinity norm is what happens to the LP norm when p approaches infinity. The induced norm is the square root of x inner product with x. The induced matrix norm is what happens when you take the maximum B norm of all the possible AX vectors for all the x's that satisfy the condition that the A norm of x is smaller or equal to 1. The spectral norm is defined as the maximum singular value of A, and the Frobenius norm is treating A as a vector and taking its 2 norm, meaning we sum all of the squares of the members of A, and then after the summation, taking square root. Question 2. Show that the induced norm of x, being the square root of the inner product of x with x, is a norm by definition. I encourage you to solve it yourself and then view the solution. Non-negativity is simple. Taking the inner product of x and x, and then taking the square root of that would always give you a positive number. Homogeneity can be derived using the definition of the induced norm. We can simply take lambda out over here because of the linearity of the inner product, and then flip this entire expression and conjugate it to the conjugate part of the inner product, taking lambda conjugate out. Then we get the absolute value of lambda squared in the square root. Taking that out of the square root would give us what we wanted. The triangle inequality is as follows. The norm of x plus y would get you up to this part using only simple cosmetic changes. Then in this part, we flipped y and x to x and multiplied y conjugate due to the conjugate part of the inner product, giving us 2 of the real part of the inner product of x and y. This is smaller than 2 of the absolute value of the inner product of x and y. And that would be smaller than 2 of the square root of the inner product of x multiplied by the inner product of y. We did this transformation using the Cauchy-Schwarz inequality. The rest is fairly trivial, and then we get that this is equal to the norm of x plus the norm of y. For a matrix A, let V be an eigenvector of A, with lambda being a corresponding eigenvalue. And so, A multiplied by V is equal to lambda multiplied by V. It means that multiplying V with the matrix A is equivalent to multiplying V with the scalar lambda. The spectral decomposition of A is defining U to be a matrix with the eigenvectors of A as its columns, and lambda to be the diagonal matrix with the eigenvalues of A on its diagonal. The eigenvalues on the diagonal of lambda will be sorted by the largest in the top left corner and the smallest in the bottom right, and the eigenvectors in U would be ordered to match their eigenvalues in lambda. Let A be a symmetric matrix. A is said to be positive semi-definite, or PSD, if it holds that for every vector v, v transpose AV is larger or equal to 0. A matrix is said to be positive definite, or PD, if v transpose AV is strictly larger than 0 for every non-zero vector v. Lemma. A matrix A is PSD or PD if all its eigenvalues are non-negative or positive. The proof of the lemma. Let A be a symmetric matrix with all non-negative eigenvalues. So for every vector x, we can look at x as a linear combination of the eigenvectors of A. Let v1 till vn be the eigenvectors of A, with the corresponding eigenvalues lambda 1 to lambda n. And so, x is equal to some linear combination sigma over alpha I vi for some alpha i's. X transpose Ax can be written as follows: the summation over alpha I vi transpose multiplied by A multiplied by the summation of alpha I vi. By changing the order of multiplication and summation, we can see that this is equal to the summation over I and this over the summation over j of alpha I alpha j vi transpose A vj. Because vj is an eigenvector of A, we can replace the A multiplied by vj by lambda j vj. We know that all the eigenvectors of A are all orthonormal, that meaning that for every I that is not equal to j, vi transpose vj is 0, and so we can simplify the summation to be the summation over I of alpha I multiplied by vi transpose lambda I vi. But we know that vi transpose multiplied by vi is the induced norm squared of vi. That is how we got this expression. But all of the eigenvectors of A are all orthonormal, meaning that their induced norm, even squared, is 1, and so we can simplify it further to get this expression, the summation of I over lambda I multiplied by alpha I squared. And so if every lambda I is non-negative, then this expression cannot be negative. But if all of the lambda i's are strictly positive, then the sum cannot be 0 as well, because we know that x is not the 0 vector, that meaning that some alpha I is non-zero. The trace of a matrix is the sum of its diagonal members. The properties. The trace is a linear mapping. It is invariant under cyclic permutation. That is a very complicated way to say that the trace of ABC is the trace of CAB is the trace of BCA. What we did here, we took one of the members from the end of the expression and moved it to the back. Trace is also invariant under transpose, so the trace of A transpose B is equal to the trace of B transpose A is equal to the trace of AB transpose. Let's show that the trace of a matrix A is the sum of its eigenvalues. So, using the spectral decomposition of A, we know that the trace of A is equal to the trace of S lambda S inverse. So what we can do, we can use the cyclic property of the trace, and we can move S inverse from the end to the beginning, and we get the trace of S inverse S multiplied by lambda. That is equal to the trace of I multiplied by lambda, which is the trace of the lambda, which is the sum of the eigenvalues, because the lambda is a diagonal matrix with the eigenvalues on its diagonal. Let A, B, and S be three matrices such that A is equal to S lambda A S inverse and B is equal to S lambda B S inverse. What is the trace of A, B? I suggest you solve this yourself and then return to the video. The solution is the trace of AB is the trace of S lambda A S inverse multiplied by lambda B by S lambda b S inverse. As we know, those two will cancel out, and we get the trace of S lambda a lambda b S inverse. Using the cyclic property of the trace, we can move S inverse back over here, and we get this expression. S inverse and S cancels out, and we get the trace of lambda a multiplied by lambda b. Because both of these are diagonal matrices, we get the sum of lambda ai multiplied by lambda bi. Let A be a matrix and f of x is a scalar function with the following Taylor expansion. We define f of a to be the same Taylor expansion but replacing x with a. As we have seen before, a raised to the power of k is u multiplied by lambda raised to the power of k u transpose. And by taking u and u transpose outside of the summation, we get u, the summation over ck lambda k u transpose, which is by the definition u f of lambda u transpose, where f of lambda is taking f of the members of lambda. And so we can see that taking a scalar function f of a matrix A is simply applying the function f to the eigenvalues of A. We can note that the trace of f of A is equal to the summation over f of the eigenvalues of A. The last question is, we need to find the eigenvalues and eigenvectors of a matrix A. We know that the determinant of a matrix is equal to the multiplication of its eigenvalues. We can notice that A is a block matrix. There's one block over here and one block over here, and it is separated by zeros. Knowing that, we can know that lambda 3 is equal to 7 and v3 is equal to 0, 0, 1, because the third eigenvector does not apply to this part of the matrix. So multiplying the matrix by 0, 0, 1 would give us 0, 0, 7, which is 7 multiplied by the original vector. And so 0, 0, 1 is an eigenvector with an eigenvalue of 7. We have this block to figure out next. We know that its trace is 4, meaning the two eigenvalues corresponding to it, their summation, is 4, and the determinant of it is minus 5, because 1 multiplied by 3 minus 2 multiplied by 4 give us minus 5, and that means that the multiplication of lambda 1 and lambda 2 is minus 5. Solving the set of these two equations would give us lambda 1 equals 5, lambda 2 equals minus 1. So for lambda 1 equals 5, we will solve a minus 5in multiplied by v1 equals 0 to find v1, the eigenvector, and we would get that the eigenvector v1 is 1 to 0, solving this set of equations. For lambda 2 equals minus 1, we will do the same, and we get lambda that v2 is 1 minus 1, 0.